this going. Okay. Okay, let me see if I can share. Okay, it looks good now. All right, so can everyone see my screen? I guess someone will interrupt me or contact me if there's a problem.
Yep, we can see you.
Okay, great. So yeah, so thank you for the introduction and the opportunity to speak at this conference. So the title of the session is Approaches to Online Quantile Estimation. So I'll introduce myself briefly and then get into the topic. So my name is Joe Ross. So my background is in pure mathematics. I used to do research in algebraic geometry until about 6 or so years ago. Actually wanted to return to LA for this conference, and it didn't quite work out as I had expected. So for the last almost 5 years, I've worked at, well, for 4 years at SignalFX, and then for the last year at Splunk as a data scientist, working on some of the algorithmic aspects, statistical aspects of some of the problems that arise in monitoring distributed applications. So some time series problems and sampling problems as well. And a lot of the discussion today is about some of the problems that have arose fairly naturally in these domains. Okay, and I'm obligated to share this slide concerning any forward-looking statements about the product roadmap and development at Splunk. Okay, so the basic problem that this talk is about is given a stream of numbers, x1, x2, and so on, to build a data structure that can basically answer two types of queries concerning the rank of an element in this stream. And so the rank of an element is simply the number of stream elements so far that are less than or equal to that number. And a related quantity is a quantile. So here Q is a number between 0 and 1. And this is simply some number in the stream with the property that its normalized rank is Q. So if you divide the number of stream elements less than or equal to that quantity X by the number of stream elements seen so far, capital N, you get Q. Okay, and there are a bunch of requirements or properties that we would like for this data structure or algorithm to have. So one requirement is that it operate online, which means that it's only allowed to see the stream once. So you see an element and then you never get to see it again. Another requirement or condition is that the length of the stream or the number of elements is not known or bounded in advance. Another requirement that you might want to place on such a data structure is that its size should not depend too heavily on the number of elements that you have seen. So surely you're not going to be able to store all the elements. Perhaps you can store something like a logarithmic factor of the number of elements in the stream so far. And of course, there are also some performance requirements. So the update operation, which basically describes how a new point is incorporated into the data structure or the algorithm, and also the operations that allow you to query for these rank or quantile quantities should be efficient, should be relatively fast. So that's the kind of setup and the basic problem that we're trying to answer. And in this talk, I'll discuss sort of some summarized history of this problem and then some recent developments and slight variations on this problem. Okay, so I will mention some applications. So you know, for this audience, it may be somewhat humorous to give applications, but anyway, so I think we probably all understand that quantiles are fundamental summary statistics, which are especially important for non-normal distributions. So if data is normally distributed, then it's enough to know the mean and standard deviation, and that basically tells you anything you might want to know about it. But for skewed distributions and other what might be considered pathological distributions that actually show up all the time in nature, quantiles are fundamental ways of summarizing those data sets. A more specific application that arises in the metric time series domain is detecting anomalies. So here you might, in some kind of anomaly detection pipeline, use some knowledge of the distribution of values that you've seen so far, and use that as some component or some aspect of declaring a point or a segment of points anomalous. Getting even more concrete, in the world of so-called observability, which is about understanding how distributed applications behave and misbehave. One approach to monitoring these and enforcing agreements across services in a microservices environment is by so-called service level agreements or objectives. And for example, you might say that your service or your application will agree to serve some very large proportion of requests within some agreed upon time, like 50 milliseconds. And of course, if you impose a static distribution, a static threshold like that, you could just count how many are above and below. But in many applications, you're also interested in knowing some details on the shape of that distribution as you move closer and closer to the really extreme executions, which may have taken quite a bit longer. And here, if you do something like a simple average, you'll get something that doesn't really reflect the typical experience because there are plenty of outliers. And I'll also try to touch on some high cardinality applications where we want to be able to answer these quantile queries on a data set that might be sliced and diced, possibly across many dimensions. Okay, so the first results, or maybe the first result in this field, is that exact answers and mild dependence on n are not compatible. So Monroe and Patterson proved a lower bound for an algorithm that passes over the data set p times. It's the pth root of the stream size. And in particular, if you want to do this online and p is 1, that means you need to store the whole stream. And their argument is a kind of nice white box attack. So the basic idea is that if you're given some fixed storage size s, then you can design an input that will, after say one pass of the data, leave you a problem as hard as answering rank queries for an input which has size n divided by s. And the idea is that once you filled up this buffer s, you have to kick somebody out. You design your stream so that the new element that arrives has the same rank relative to that reservoir as the thing you just kicked out, which means that you cannot make any comparisons between the thing that was just kicked out and the thing that was just added. And you design your stream so that is always the case. And then if you're trying to answer something like a median query, your median will live somewhere in one of these sets on which you can't make any comparisons. But to determine what the actual median is, or to determine any other precise rank quantity, you will need to have a procedure that works on an input of size n divided by s. And so this leads us to, since we generally won't be able to store the whole stream, to formulate an approximate version of rank and quantile problems. And so we say that a data structure can answer epsilon approximate rank or quantile queries. If we don't get the answer, we don't necessarily get the answer exactly, but in quantile space or in rank space, the error that we incur is bounded by some quantity, some small positive quantity epsilon. And then once you have this kind of formulation, you can also ask that the data structure that you produce can be tunable or live in a one parameter family parameterized by something related to epsilon. So I want to make a couple of comments about the approximate condition. So one is that this is formulated in quantile space, not value space. In other words, the guarantee is that the estimated 95th percentile lives between the actual 94th and 96th percentiles, in the case where epsilon is 0.01, not that the estimated 95th percentile is within 1% of the true 95th percentile. And there are several reasons for this, or just observations about this. So this is a formulation that makes sense for streams drawn from arbitrary ordered sets, not just real numbers. This is a formulation that is invariant under monotonic transformations of the data. So if you have a concept of, or if you have a structure that guarantees 1% error, and then all of a sudden the data is shifted by some large positive quantity or some negative quantity, whether or not you achieve that guarantee is not invariant under that transformation. And so it's kind of hard to reason about what this really means. And it's also a somewhat less interesting problem, which is maybe not a reason to argue against it. But anyway, for guarantees in value space, there are some simple solutions that basically amount to enhancing fixed bin approaches. And it's maybe worth pointing out that guarantees in quantile space can be arbitrarily bad in value space and vice versa. So these may seem like similar problems, but they're actually quite different. So by way of motivation, I would like to imagine that we could store the whole stream and then produce a compact read-only data structure. And so what we might do is, if we had all of the data, and this is not a very big data set, if we wanted to answer quantile queries exactly, we would just say, well, I'm gonna pick every fourth element, and then maybe I'll also record where this element lives. So I record the fourth value and say that it's greater than 3 elements. I record the 8th value and say it's greater than 7 elements, and so on. And this will allow me to get some reasonable error. Of course, the problem is that since we're not able to store the whole stream and we don't know what the rank of an element is when it arrives, we will generally need to store more information in order to continue to answer these rank queries with some guarantees in the streaming setting, because we don't know what the rank will be once all the data has arrived. Okay. So there's another property which comes up called mergeability. And this basically says that if you form one of these gadgets on stream 1 and form another one on stream 2, then there is some operation that merges them into another data structure of the same type. And it doesn't have to be exactly the same as what you would have gotten by applying the data structure to the streams concatenated, but at the very least, the error guarantees should be similar. And in some sense, the data structure should be hard to distinguish from what you would have done had you just seen the stream all at once. And so this has a kind of obvious motivation from distributed computing, where you might have separate machines, each computing some summary and then writing to some central storage. And if maybe they're not able, maybe they don't communicate, but you still need a way of merging each of their views of the world. And so that's one very practical scenario that motivates this sort of abstract condition. And then in the thinking more about particular applications, when you have summaries over distinct windows of time to do anomaly detection, you're often interested in producing a summary of a larger window, or you might want to do this across other dimensions. And the mergeability is then necessary to allow you to answer more sophisticated analytical queries. So you might have one of these structures in every minute, but want to be able to answer queries about hour-long, quantiles over an hour-long summary statistics as well. Okay, so that's another condition, and not all of the structures will have this, but it's something kind of waiting for you and lurking when you think about implementing some of these things in practice. Okay, so it's not all bad, or it's not all negative results in the Monroe-Patterson paper. So they also provided an algorithm with smaller size that succeeds with extremely high probability. And just to fix ideas, let's say we're trying to find the median of a stream. So the idea is that we will maintain some number S of consecutive elements, and also the counts of elements below and above this S element set. And we'll call those counts L and H for low and high. And then you can view the progression of this algorithm as the stream arrives as a random walk of the quantity H minus L, which is basically describing how lopsided this S element set is, or how lopsided its two sides are. And you will always find the median just by looking in S itself, if you can guarantee that this structure doesn't get too lopsided. In other words, the difference between H and L is less than S minus 1. And then you can use that, assuming equal transition probabilities in this random walk scenario, the first S squared steps are extremely likely to stay within S minus 1 steps of the origin. And so just as in the previous case where we got this n to the 1 over p by analyzing what might happen if we kept S slots and had an adversarial adversary giving us indistinguishable elements. The fact that we have this S squared allows us to reduce this to a problem of size not n over S, but n over S squared. And so this gives us a more favorable asymptotic size compared to the previous attack, which only allowed us to reduce to a problem of size n divided by S. So it's a complementary positive result in the same paper. Okay. And then a bit later, there was another approach developed by Greenwald and Khanna. And by the way, all of these papers will appear in a references slide at the end. And the idea here is that we'll maintain a sketch that consists of an ordered set of stream elements and some additional data, and that data is giving us bounds on what their ranks might be in the stream overall. Okay, and so the quantities that we track are triples. So there's a VI, which is some stream element that we've actually observed. There's a quantity called GI, which is the difference between a minimum bound on the current rank of that element and the current minimum bound of the current rank of the preceding element living in this sketch. And then also something, quantity called, which they call delta I, which is the difference between a maximum bound and a minimum bound on the rank of that element VI. And so in the construction, we don't actually store, we don't actually compute the quantities R of E themselves, but rather these differences. But these differences are enough to allow us to answer quantile queries. So you can imagine adding up the GIs, for example, and then also incorporating what the delta I's are. So we don't have to have the R's explicitly, but we have them implicitly because we have differences. And so if you have one of these gadgets, so an ordered set of stream elements together with this auxiliary rank information, then the error is bounded by the maximum of these two auxiliary quantities divided by 2. That's kind of how it's designed. If you want to add, I think I called it d.add on one of the first slides. If you want to insert an element, you insert the triple V1 and then some quantity that reflects the error that you would like to be guaranteed and the current size of the stream. And then there's also a compression or merging mechanism that keeps this whole data structure relatively compact. And so if you imagine you just keep inserting things and never merge them, you'll just have a copy of the stream with a bunch of auxiliary information, and that's not really going to help you. So the compression tries to merge consecutive tuples so that the sum of the quantities GI and delta I are approximately 2 times the desired error times the current stream size. And when you merge tuples, if you kind of think about it for a minute, the GI quantities will add. And so basically, periodically, you will sweep through this data structure, and provided that you can merge things and still maintain that the sum of the GIs and the delta I's is small enough, then you do that. And then the question becomes, well, how many elements do you need to actually keep if you want to be guaranteed that for all of the tuples in the structure, the sum of the G and delta quantities remains relatively small. And by some analysis, they showed that it's at least asymptotically the logarithm of the desired error times the stream length divided by the desired error. Okay, so that was Greenwald and Khanna. And there's now an essentially optimal solution to this problem, which is an extremely an intricate and careful hierarchical sampling device. And so the basic ingredient is called a compactor. And by the way, K, L, and L are the authors, which you'll see on the last slide. A compactor holds K items, each of some weight W in order. And then it has an operation called compaction, which spits out k divided by 2 items, each with weight 2w. So basically, the compactor represents an item has been seen about w times, an item or a similar item has been seen about w times. And then the operation of throwing away information is basically keeping only the even ones or only the odd ones with equal probability and just multiplying the weights by 2. And so if you imagine we have some elements, some value A with associated weight W all the way through F, then if we compact this and choose the even ones, we'll keep B with associated weight 2W. Okay, and you don't actually have to keep the weights because they're constant in each compactor, but just as a way of representing it more clearly, I add the weight as an annotation for all tuples. And then the device consists of a bunch of these. So there's in weight 1, you have k elements for some k, which you work out later. And then you have slightly more elements of weight 2, and then slightly more elements of weight 4, all the way up to k times c to some power elements of weight 2 to the h. And so the bottom one, where all the elements have weight 1, is seeing the stream. It fills up, and then it basically passes half of its elements with weight 2 up to the next one, and now it's empty. And then it starts to see more elements, it does the same thing, and it passes it up. And then eventually the thing in weight 2 is full, and it has to do the same thing, and it passes it up to weight 4, and so on. Okay, I mean, that's something you can do. And what they proved is that this is worth doing. So basically, by expressing the number of levels and the number of compactions in terms of the weights, which are exponential in the level, and also the size of the stream, you can put yourself in a situation where you can apply Hofding's lemma. So basically, the error that you incur with a single compaction can be described in terms of some multiple of a random variable which has 0 expectation and is bounded. And so when you apply Hofding's lemma, you end up getting a favorable result. And so it's a fairly straightforward, elegant argument, which I won't repeat here, but you can look at the paper. And basically they achieve something that matches the Greenwald-Khanna size probabilistically. And the construction is somehow simpler, and the arguments are simpler, and this data structure is also mergeable, basically because you merge the sorted arrays in each level. So you merge things that have the same weight and sort them. Okay, and then there are some enhancements to get the size that are really needed to get the matching Greenwald-Khanna size. You can replace the lower levels by some sampling device, and then in the higher levels, you don't allow them to grow exponentially in that parameter c. Eventually, you keep them constant. But these are, and the argument gets a little bit more involved, but conceptually, it's kind of the same thing. And then there is also this option of passing that whole device, which is going to produce for you some stream with possibly very large weight elements to a Greenwald-Khanna sketch. And you may lose mergeability because the Greenwald-Khanna thing is not known to be mergeable, but you will get some optimal size. But that's maybe not a super important detail. Okay, so I want to mention a variation on the epsilon approximate conditions, because there are many applications where you don't really care about estimating quantiles uniformly accurately across quantile space. You may care a lot more about accuracy near the tails. And so there's a data structure which, as written, only applies to streams of real numbers, but there are ways of modifying it that would allow it to apply to other streams, called the T-digest. And one of the innovations or the ideas is that you prescribe the desired accuracy as a function of where you are in quantile space. And so kind of similar to the other approaches, you're maintaining a sorted list of centroids. So V is some value and W is a weight that represents the number of points that you see near V in some sense. And there's a kind of similar insertion and merging mechanics to the other structures I've mentioned. And then the new thing is this idea of the scale function. and it's a function from quantile space to the real numbers. And what it prescribes is that if you have a cluster, or if you have a centroid that occupies some region in quantile space, say bounded by Q1 and Q2, then if you look at k of the scale function k evaluated at Q2 minus k evaluated at Q1, that is less than or equal to 1, okay? Or the cluster itself only has one element, okay? And so I'll go through some interesting examples. So let's do some boring examples first. So if you use the scale function 10 times q, that is basically saying divide the data into 10 equally sized bins, okay, and do this in a dynamic way, okay? And then you can use your imagination and have some more zeros, okay? So look, I have another great scale function. It's 1,000 times q, and this is basically saying try to divide the data into 1,000 bins of equal size. Okay, so that is not very interesting because that will, at least from the standpoint of getting higher accuracy towards the tails, that is similar to the epsilon approximate condition, which just says uniformly give me answers that have a certain accuracy in quantile space. But there are some more exotic scale functions, and so these are some formulas. But the important thing is that if you look near 0 and 1, they are increasing much more rapidly. And if you look at the growth condition, this is saying that the clusters or the centroids have to be kept very, very small near 1 and near 0. Whereas if you look at something near the median, especially for K2, you will allow that cluster to get relatively large. The motivation being that you don't particularly care about accuracy near the median, but you're much more interested in accuracy near the tails. Okay, and there are a few other scale functions, but they were basically all symmetric, and so all these nonlinear scale functions give you error that looks like some function of the smaller of q and 1 minus q. But as I just said, especially in the case where the data has serious positive skew, you may want asymmetric accuracy. So you may care a lot more about accuracy towards q equals 1 and care relatively less about accuracy near q is equal to 0. And it's a condition, or it's a property of the scale function that the collection of centroids will continue to satisfy the growth condition of the scale function after you insert some new data. So if some data lives near the median, it's allowed to be that cluster is allowed to be relatively large. But as you start making insertions, it will slide around in quantile space, and all of a sudden higher accuracy may be demanded of it. And so you need to know that even if it slides around, it still satisfies the growth condition. And so I developed a term for this. It's maybe not that creative, but it basically says a scale function will accept insertions, and all of its scalar multiples will accept insertions. And that turns out to be equivalent to for every insertion, whether it's on the right or on the left, the difference in the values at the endpoints goes down. So here, Q1 and Q2 should be thought of as the endpoints of a cluster in quantile space before an insertion, and Q1 prime and Q2 prime would be the endpoints of that cluster after an insertion. And there are basically two scenarios where you move it, where it slides to the right and where it slides to the left. And this turns out to be something that you can work with a little bit. So one consequence of this characterization is that decent scale functions must be continuous, in fact, differentiable. And this is sort of a proof of that. So if you have a point of discontinuity, I think you can see that one. What you have to do is just zoom into the function so that it grows. Its growth is relatively small compared to that discontinuity. And then you just have to fabricate some cluster and insertion that pushes something over the discontinuity point. And then by construction, the k evaluated on Q2 prime minus k evaluated on Q1 prime will be a bit larger than k of Q2 minus k of Q1. And a kind of similar argument shows differentiability. And this suggests a certain construction to produce reasonable scale functions which have asymmetric accuracy about the median, which was not available in the original T-digest paper. And that's simply, well, if you know they have to be differentiable, pick a point. How about Q is equal to 1/2, and draw the tangent line, or replace the function, the scale function by its tangent line at that point, say on the left side of the distribution, left side of quantile space. And of course, we didn't prove that differentiability implies decency, but to verify it, there's a fairly simple characterization, which basically says that two functions derived from the scale function are non-increasing in Q for any value of alpha, and this turns out to be a pretty straightforward calculus exercise. So we verified that these behave well with respect to insertions. Okay, and then you can ask, well, what is the benefit? And so this is meant to show the benefit of changing from the logarithmic scale function to the version where you glue its tangent line at 1/2 for the left side of the distribution, as shown before. And so in the first column, you have the error. The second column in quantile space. The second column normalizes the error by the smaller of Q and 1 minus Q. And the third column is telling you roughly how many centroids were kept. And I use delta equals 100, so we should expect something on the order of 100 centroids. The first row is the usual symmetric scale function K2, which is going to be very accurate near the minimum and the maximum. And the second row is the asymmetric one, where we've made the scale function linear for Q less than 1/2. And basically, to summarize what this says, and I can also explain the axes, what it basically says is if you look at the right column, it's saying, well, we save about 40% memory because we reduce the number of centroids from about 70 to about 40. We basically keep the same accuracy on the right side of the distribution. So we have the same accuracy near Q is equal to 1. But on the left side of the distribution, we have the error profile more of a linear scale function. So we've allowed ourselves to trade off some memory. We've gained some memory back in exchange for giving up accuracy where we don't care about it, because there are applications where you don't really care what is the difference between the first and third percentile, but you care a lot about what is the difference between the 97th and the 99th. Okay, so that's a kind of summary of how it behaves, and then it's also very interesting to look at it on skewed data sets. I'll just mention briefly, since I have only 5 minutes left, that after the asymmetric T-digest was developed, there's a relative error variant of KLL that came out, just posted on the archive. And again, the motivation is that if you're near the boundary, if you want to estimate the first percentile, having error 0.01 is not so interesting. And so there's a variation on the rank condition that is strictly harder to achieve. And so the idea is that you have the same type of compaction procedure, and you have a hierarchy of them, except you don't just choose even or odd. But for example, if you want to keep accuracy towards the right side, you will divide up in each level the array into a right half and a left half. You will never compact the right half, and then you'll divide up the left half into some chunks. You will always compact the first one, which means you will always take every other element. Half of the time you will compact the second chunk, take every other element from it and double the weights, and so on. And then it's the analysis is quite a bit more involved, but you eventually get this relative error guarantee with slightly worse space, which is provably needed. And then I think because I have just a minute left, I'll just leave this here. This is the final slide of content. this is a rather different approach that only applies to real numbers. But maybe I won't say anything about it, but it's aimed at the high cardinality scenario. So I'll stop there and check the chat to see if there are any questions. Okay, so I see one.
Yeah, I was going to say that you could actually move to the Q&A for the questions, which is the same question.
Okay. Oh, I see. The slide deck, the question is if the slide deck will be shared. Yes, I think it's already shared.
Cool. And you want to share some, I know you kind of touched on this in the beginning, but you want to share some information as far as where people can go to get some more information, or possibly even contact you if necessary, some of your contact information if necessary.
Sure. Actually, yeah, my contact information is not in the deck. So these are the main references for the talk. And then if you look in their bibliographies, I think you'll basically cover the subject pretty well. But these were papers that I found interesting. I'll be happy to add my email address to my WOVA profile if it's not already there. But anyway, it's josephR@splunk.com if you're listening.
Well, Joseph, that was very insightful. Thank you so much for being a part of DataCon LA 2020. Thanks for making the time, coming down and sharing your knowledge base with us. We really, really appreciate it. And thanks for a great presentation. That was definitely a lot to take in, but you shared the knowledge well.
Well, yeah, thank you, and thanks for the opportunity to speak and for listening in.
Okay, and that would conclude the session. Thanks everyone for attending, and thanks again, Joe.